In this lecture, we're going to talk about vision. We'll cover the basic principles of light, including frequency and wavelength of light, reflection and refraction of light. We'll discuss the basic functional anatomy of the eye, including how light enters the eye, visual defects, and how we see color. And we'll also talk about the effect of lighting on physiology and performance in the workplace. First, let's talk about the properties of light. To understand how light plays a part in human factors and work environments, we first need to understand how light itself works. Light is an electromagnetic wave, or more specifically, particles that exhibit wave-like properties. The amplitude of the light wave is what we perceive as brightness, and the wavelength, in nanometers, is perceived as the hue, or color of the light. When we talk about light, we're referring to a narrow spectrum of the electromagnetic radiation spectrum. This is going to include visible light as well as ultraviolet and infrared light. The visible light spectrum ranges from about 400 to 700 nanometers, which encompasses colors that range from violet with the shortest wavelength of 380 nanometers to red with the longest wavelength of about 700 nanometers. Infrared light has a wavelength greater than that of red light, while ultraviolet light has a wavelength that is shorter than that of blue light or violet light. Refraction is the change in direction of propagation of a wave due to a change in its transmission medium. Think of going from air into the lens of your eye or your glasses. A diopter is the refractive power of a lens, with one diopter being a lens that can focus parallel light rays to a point 1 meter from its central axis. Effectively, this means that the dioptric value of the lens is the reciprocal, or 1 over the focal length. Our eyes have a refractive power of about 59 diopters in a relaxed state, with the cornea accounting for about 40 diopters and the lens the remaining 20. This gives us an effective focal length of about 16.9 millimeters. Since the cornea and lens are convex, they have a positive dioptric value, while concave lenses would be negative. When light enters the eye, it's refracted through the cornea and the lens and then focused on the retina. The pupil contracts and expands to adjust the amount of light entering the eye, acting similar to the aperture of a camera lens. If you're a photography nerd, you'll be impressed to know that the pupil can adjust for a staggering 30 stops of light. Accommodation is the ability of our eyes to focus on near objects. This accommodation allows us to increase the refractive power of the lens, as a more spherical lens equals more accommodation. For distant objects, our eyes relax and adjust the refractive power of the lens to suit the desired focal length. So how does accommodation in our eyes work? Well, it happens with the contraction of the ciliary muscles, which enables the lens to become rounder and have more refractive power. Essentially, the muscle squeezes the front of your eyeball right where the lens is, and just like any other sustained muscular contraction, this can lead to fatigue. When the ciliary muscles are relaxed, the suspensory ligaments pull the lens back into a thinner, flatter shape, which allows us to see distant objects better. This accommodative power allows us to increase our refractive power by about 15 diopters. This, however, decreases with age to the point where we can't effectively accommodate anymore, which is a condition known as presbyopia. Since accommodation doesn't happen instantaneously, you can experience a temporary blurriness with a sudden change in gaze. You can try this by rapidly moving your hand towards your face and focusing on it, and then move it away and focus on it again. The image of your hand should briefly be out of focus before coming into sharp focus. Eye strain can be caused by focusing on near objects for too long. Because focusing on close objects requires the ciliary muscles to contract and provide accommodation, it can lead to this eye strain or fatigue, which can result in the inability to maintain that focal length, blurred vision, and headaches. Let's take a look at a couple of common visual defects. Hypermetropia is when light is focused behind the retina instead of on the retina. This causes farsightedness. We would correct for this with convex lenses, which increase refractive power and focus light closer. For glasses or contacts, this would be a positive diopter value. Myopia, or nearsightedness, is when the light converges ahead of the retina, and this can be corrected with concave lenses, which increase focal distance. This would be a negative diopter value for corrective lenses. Astigmatism is a condition referring to a refractive error that results from unequal curvature of the surface of either the cornea, the lens, or both. This results in blurred vision at all distances and makes it harder to shift vision between different focal lengths. Spherical aberration refers to how the outer region of the lens focuses light at a point slightly ahead of or behind the mid portion of the lens. This causes vision to be blurred. However, our brain integrates images from both eyes, which it then processes and creates a crystal clear image. Positive spherical aberration, where the outer portion of the lens focuses light slightly ahead of the center of the lens, is common in healthy eyes. And during the process of accommodation, the increased sphericity of the lens leads to a shift to negative spherical aberration. Vergence is the movement of the eyes together or away from each other, and can be either convergence, where the eyes shift towards each other to focus on an object that is very close, think about crossing your eyes, and divergence, where the eyes face in opposite directions. This is often used when scanning objects that are in the distance. Convergence is necessary to focus on close objects and works with accommodation to improve our focus. Excessive convergence at a workstation can lead to fatigue and makes it harder to focus on the task and leads to eye strain. The natural distance where vergence becomes necessary changes with gaze angle. So as you look up or look down, it'll change how far away from an object you need to be before convergence is required. Downward gazes require less vergence for a given horizontal distance than looking forward or looking up. Ergonomically speaking, objects below the line of vision are more comfortable to view because it requires less convergence. When viewing close objects like a computer monitor, we should try to lower the object to minimize the required vergence. To do this, we should be no closer than 1 meter when looking straight ahead, or 80 centimeters when looking down at a 45-degree angle. The closer the object, the lower it should be. We also want to avoid accommodation traps. These happen when objects are right at the point of accommodation, which will lead to constant adjustment and increased fatigue. Visual acuity refers to the sharpness of our vision, and we typically assess it by measuring the ability to discern letters or numbers at a given distance according to a fixed standard. This type of test shows the ability to discriminate in fine detail and is dependent on accommodation. There are many different ways we can measure visual acuity, such as the Snellen test, and you may have seen a few of these at the optometrist. The meaning of 20/20 vision, for example, is that a person with 20/20 vision can detect a critical detail at 20 feet that a person with healthy vision could detect at 20 feet. 20/40 vision would mean that you need to be within 20 feet to detect an object that would normally be seen from 40 feet away. This means you're likely going to need glasses. The retina is the region of light-sensitive receptors at the back of the eye. There are two types of receptors: rods that are light-sensitive and are responsible for night vision, also known as scotopic vision, and we have approximately 120 million rods in the eye. Cones are color-sensitive cells that are densely located in the fovea and provide color vision, known as photopic vision. We have substantially fewer cones with only about 6 million. The Fovea Centralis is a small central pit composed of closely packed cones in the eye in the center of the macula. This is responsible for our sharp central vision. It's necessary to provide highly detailed images and is useful in tasks such as reading and driving. Damage to or genetic variations in the fovea and cones can result in color blindness. Damage to rods primarily decreases sensitivity light, but since we have far more rods than cones, if we damage a small section of the eye, we're likely to retain much of our visual ability. We have 3 different types of cone cells with sensitivity to different wavelengths. Any given color is perceived by the distribution of firing of the cone cells in that area, and color blindness occurs if one set of cells is missing or damaged. Color blindness is more common in men than women, with deuteranomaly and protanomaly being the most common, and resulting in the ability to correctly perceive the color red to varying degrees. As a note, the suffix anomaly means that the cone cells are present but impaired, while the suffix opia means that the cone cells are not present at all. Some examples of what someone with these visual impairments might see are simulated in this image. And if you don't have any visual impairment, you'll be able to clearly distinguish shades of red, green, and blue, well, greeny blue, and clearly make out the number 2 in the middle. Deuteranopia and protanopia are going to see in shades of blue and yellow. The rarest color vision impairments are tritanopia and tritanomaly, which are blue-yellow deficiencies, as well as achromatopsia, which is an extremely rare condition that results in monochromatic or black and white vision. Because rod cells are mostly distributed in the periphery and cones are in the fovea, we can't easily identify color in our peripheral vision. Rods also have less acuity than cones, which means that what we see in the peripheral vision has less detail. In the workplace, this is a good reason to use flashing warning signals rather than lights that change color to indicate an error. Across the color spectrum, we're most sensitive to green and blue-green colors, and least sensitive to pure red and blue. At any given illumination, green is naturally brighter than blues and reds of similar intensity. This is why night vision goggles, for example, are green. It increases our ability to discriminate features as we're most sensitive to green colors. Importantly, both our rods and cones are most sensitive to green, which results in higher acuity and a high sensitivity to changes in brightness. Red is the color we're least sensitive to. If we want to preserve night vision, not the goggles, but just seeing in the dark, we can illuminate a room or sign with red and not worry about losing our ability to see in the dark. Well, sort of. Really, the goal here is to balance the activation of high sensitivity, red insensitive rods with that of low intensity but red sensitive cones in the fovea. For example, we might use this in a dark room while we're developing film to be able to see, and then when we leave the room, we won't lose our vision. Purkinje Shift happens as we switch from cone to rod vision, from day to night. Shorter wavelengths appear brighter and longer wavelengths appear darker. This means that green light is going to be brighter at night and red light is going to be darker at night. Take a look at this simulated view of a geranium in bright light, which relies on photopic vision, at dusk, or mesopic vision, and at night using scotopic vision. Night vision is also more sensitive than day vision. At night, we primarily see with rods because they're more sensitive to light. Our most light-sensitive ranges are yellow-green during daylight and pure green at night. Whether it's night or day, we're not very sensitive to red lights or objects. And at night, sensitivity to red is near zero. For this reason, you may have noticed that new fire trucks are now yellow instead of red, and most high-visibility clothing and reflectors are yellow-green. Now let's talk about some of the dangers of blue light. As you may have noticed from the new trend of blue light glasses, blue light can have detrimental health effects. The light from cell phones, computer screens, and televisions have a higher concentration of blue light than natural light does. Blue light affects the production of melatonin, which is an essential sleep-regulating hormone. This is because retinal ganglion cells contain melanopsin, which is a photosensitive pigment that helps to regulate the circadian rhythm by communicating directly with the suprachiasmatic nucleus, which is often referred to as the body's clock. Melanopsin is most sensitive to blue light wavelengths of approximately 480 nanometers, and is less sensitive as wavelength increases or decreases. The suprachiasmatic nucleus prevents the release of melatonin from the pineal gland during daylight hours, which regulates the circadian rhythm. This means that to promote a normal circadian rhythm, we want to increase red light at night and decrease blue. Shifts in our circadian rhythm can have devastating health effects on wakefulness and organ function. Research has shown that long exposure to electronic displays can suppress melatonin release after about 2 hours of exposure. This means that to reduce blue light exposure at night, we should avoid fluorescent lights and color shift our electronic displays, such as TVs and computer screens, through the use of blue light blocking glasses or a computer application like Flux, Windows Nightlight, or Night Shift on Mac, which can be used to shift the color spectrum of the monitor towards red. Now let's take a look at lighting conditions. Luminous flux, which is measured in lumens, refers to the total light emitted by a source. Illuminance is the light falling onto a surface, measured in lux, which is lumens per square meter. And luminance, not to be confused with illuminance. Luminance is the light reflected by a surface, measured in candela per square meter. Now here's a weird measure. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 10 to the 12 Hz, and that has a radiant intensity in that direction of 1/683rd watt per steradian. Or alternatively, and a lot more likely to be used, 1 candela is roughly equivalent to the luminous intensity of a common candle. Light affects our performance and can have a wide range of effects, including headaches, eye strain, neck, back, and shoulder pain caused by straining to see items in poor lighting, falls, trips and slips, dropping materials or tools, and even depression in the case of insufficient or gloomy lighting. Think of seasonal depression. The main causes of lighting-related problems are going to be insufficient light, glare, improper contrast, and poor distribution and flicker of light. Lighting surveys can be a useful tool to identify areas of good lighting and poor lighting so that the conditions can be addressed or work can be planned to take place in areas with appropriate lighting. From a business perspective, studies have shown that performance time decreases with increasing amounts of illumination, up to safe working levels, and that the frequency of errors decreases with the coinciding increase in illumination. Glare is another potentially unfavorable component of lighting. Direct glare comes from light sources in the visual field, while indirect glare is light reflected from sources out of the visual field. Indirect glare can be either specular reflections or diffuse reflections. Specular reflections, where light is reflected at only one point that is visible to the person, such as on smooth surfaces like a mirror, can be essential to job performance. For instance, mirrors on a car to provide vision behind you. But you can also create areas of high luminance that can cause discomfort and disrupt work. Think of a bright light reflecting in a mirror. Diffuse glare is light that is reflected on matte surfaces like a white wall, and it diffuses the light so that the light from all points on the surface reach the viewer. This can be a good way to eliminate bright reflections and improve lighting conditions. Glare may lead to discomfort, annoyance, or pain, and can even lead to disability. For an extreme example, think of the light emitted by a flashbang. It will cause intense pain and temporary blindness by overstimulating the rod and cone cells. Glare can reduce our ability to perform a task. Think of driving down a bright sunny road with water on the surface. It's going to reflect in your eyes and make it difficult to see oncoming traffic and features of the road. Additionally, there's a unique physiological response called phototropism, which is our natural tendency to gaze at bright objects. Think of a deer in headlights, or Donald Trump staring into the sun during his inaugural speech. We can also have temporary blindness resulting from a saturation of our visual senses. We have some good strategies for improving lighting in the workplace, however. We can begin by reducing display reflections by utilizing indirect lighting systems, blinds and drapes to block direct light, and low wattage direct light on documents, ensuring that they're not brighter than the screen. We can also utilize polarized lenses, either on sunglasses or corrective lenses. In unpolarized light, which is just ordinary light, the fluctuations in the electrical field occur randomly in all directions. When light hits a horizontal surface, like water, your desk, or the road, it's horizontally polarized and is reflected, causing glare. Polarized lenses are designed to only allow vertically aligned light to pass. This eliminates reflections and decreases the luminance slightly. Polarized lenses have been chemically treated with a compound whose molecules naturally align parallel to one another and are oriented so that they absorb light that is not aligned with their primary axis, in this case, vertical. This means that we're going to get a nice clear image with no glare. Light flicker is another persistent risk factor in the work environment, particularly in office and factory settings. Quick repeated changes in light intensity happen when the voltage supplied to a light source changes. This is not usually a concern with incandescent light bulbs because the element doesn't cool quickly enough to change intensity during the on-off cycles of alternating current power. In ballast-based light sources, such as fluorescent lights, alternating current produces light flickering at 120 Hz, which is twice the power line frequency of 60 Hz in North America, or in many other countries, light flickers at 100 Hz due to the 50 Hz power line frequency. This flickering at double the line frequency is due to the fact that light operates on a voltage differential, since alternating current swaps between plus 120 volts and minus 120 volts, or plus 240 volts and minus 240 volts. It means that the light will have 0 volts twice every cycle. Most people can't notice flickering at 120 Hz, but we can see it at 50 to 60 Hz. Ever since fluorescent lighting was introduced to the workplace, complaints about headaches, eye strain, and general eye discomfort grew rapidly. Even though we may not consciously perceive the light flickering at frequencies as low as 60 Hz, our eyes are still responding, and this can lead to fatigue. To eliminate this effect, we can increase the frequency of oscillation to decrease the effect of the flickering. This is done by installing high-frequency ballasts in fluorescent lights that operate at frequencies of 20,000 Hz or higher. The use of these high-frequency ballasts resulted in a 50% drop in eye strain and headaches when implemented in an office environment. One growing concern, however, is that the increased use of LED lighting may lead to similar effects as the early fluorescent lights, because LED lighting systems typically produce a stroboscopic effect at a 100 Hz frequency. No matter how you look at it, lighting is an essential component of the workplace, and it's our job to make sure that we create a suitable environment so that people can be productive and work safely.